All right, last class, we left off on this collision theory thing, and I wasn't running at full capacity, so my brain was like, yeah, I know it's this C one, but I don't know why C is better than B, and the reason C is better than B is because you can't flip them. So it has to be this particular orientation, whereas molecular hydrogen and iodine, you can flip-flop them. So C is going to have the smallest orientation factor because it needs the most precise lineup. So we've been talking about big, broad, overall reaction mechanisms or reactions, and we're moving on to reaction mechanisms. So oftentimes reactions don't occur in one step. They'll occur in a couple of small steps. And there's actually a lot of time and energy that's invested to figure out some of those mechanisms. So our chemical equations have looked something like this, right, where we just have reactants and products, and it doesn't show us if there's anything happening in between there. So to us, it just looks like this one hydrogen has to run into two iodine chlorides, or iodine monochlorides, chlorines, and then they, boom, you get products. In reality, that's probably not what happens. And so a reaction mechanism is the steps or the process of the reaction. So an example of, right, something that is a process, if I go to the grocery store to buy milk. There are steps involved in me going to the grocery store to buy milk. We're all somewhat familiar probably with the process of going to the grocery store. That's not an unfamiliar concept to us. And so you can probably fill in some of the details of what it looks like for me to go to the grocery store. And elementary steps are the pieces, the steps of the journey, or of the reaction. So that would be for going to the grocery store to buy milk. I get in my car, I drive to the store, I get out of my car, I buy the milk, I get back in the car, I drive home, I get out of the car. Something like that. Maybe with a couple more steps in there, but that's kind of the basic idea. The reaction that we were looking at just a little bit ago has two steps. So we've got an initial step where a hydrogen molecule reacts with an iodine monochloride and forms these products. And then we get another iodine monochloride reacting with HI, the hydroiodic acid. And that's how we get our products. When we are putting together a reaction mechanism, it's important that the steps add up to the overall reaction. So we need to be able to cross things out from this two-step process to show that it's consistent with the overall reaction. Otherwise, it would be a different reaction. So a way that we would do that, maybe looking at things that are on the left side of the second step or the right side, just canceling things out left and right. So for example, we've got an HI up here, we've got an HI down here. Those would cancel out. We've got an ICL, another ICL. So we could combine those two sides, and it should look like what we saw before. That would just be us checking that these steps are consistent with the overall reaction. And in this process, we also have, oftentimes, reaction intermediates, things that are formed in one step and then consumed later. So HI is an intermediate for this reaction mechanism. It doesn't show up in our overall reaction, but it is crucial to forming the products. So our reaction mechanism shows us all of the steps and how they occur at the molecular level. So we're zooming in on individual processes. It's like a play-by-play of what's happening in the reaction. And kinetics can help us determine the mechanism of the reaction. So for example, we might measure the kinetics of the overall reaction. That can give us some help. And then we can, once we have that overall reaction kinetics figured out, then we can start to play around with some ideas about how we might write a mechanism that's consistent with those kinetics. So despite what we're going to see on the next couple of slides, keep in mind that we still have to measure for a reaction, we still have to measure the kinetics. We have to determine the kinetics experimentally, despite what we're seeing coming up here. So when we're dealing with elementary steps, so steps in the process, not for the overall reaction, just steps in the process for the overall reaction, steps in our mechanism, we can describe those elementary steps based on how many things react. And I'm going to move these over. So we've got unimolecular, just one reactant particle. Bimolecular, which is two reactant particles. They can be the same identity, they can be different identity. We can also have termolecular. These would all be good words to have in your vocabulary. Termolecular involving three particles. And as says here in the slides, those are very rare because you're getting three particles to collide at exactly the same time. That's not going to happen very much relative to two particles colliding. And we have rate laws. Again, these are rate laws for elementary steps. Rate laws for elementary steps can be deduced from their equation. So we can propose what's going on in the reaction because we're looking at one individual collision. So when we're looking at elementary steps, like this A plus B goes to products, we know that the way that this proceeds is A and B are colliding. And so it's dependent on the rate of A. It's also dependent on the rate of B. So rate equals K, concentration A, concentration B. This only works for elementary steps. It doesn't work for an overall reaction. So that's one thing that's kind of nice about when we're dealing with elementary steps. We can just come up with the rate law. Oftentimes, if you've got a multi-step reaction, especially one with intermediates, one of the steps is going to be a lot slower than the others. We call that the rate determining step. That determines the rate of the reaction. You might be able to imagine a scenario where you need to buy school supplies. Somebody else is paying for your school supplies. You're ready to go to the store, buy those school supplies. You getting in the car, getting into the store, not a big deal, hopping on Target.com or whatever. You can do that, no problem. And whoever's got the money is like, well, hold on, yeah, I'll get to it, and then they get distracted, and hold on, yeah, I'll get to it, and then they get distracted, right? That would be the rate determining step for you going to the store to buy school supplies. So that's kind of what's holding everything up. And in our reactions, there's usually a rate determining step or a rate limiting step, even if it's a fast step. We'll be talking about things as fast and slow. These are relative to each other, not like, these aren't like quantitative labels where it's like it's got a certain rate. It's just like in this possible mechanism, this top one is slower than the one that's on the bottom. So that's the one that's holding up all the traffic. So let's say that we get this, we have this equation. That's our overall equation, overall reaction. And we figure out experimentally this rate law, that the rate is equal to the rate constant times concentration of NO2 squared. Could this be a single step reaction? Maybe. Probably not. If this was a single step reaction, we would probably expect to see just concentration of NO2 times concentration of CO instead of NO2 squared. So one possible mechanism that we could use for this is that we have an initial step of NO2s reacting with each other. It forms an intermediate. Two intermediates. Where's the NO go? Anyway. And then we react that. Oh, the NO is one of our products, my bad. Then we have a CO that comes in, and this is a fast step. So as soon as this NO3 is generated, it's going to get consumed or used up by that CO. So the concentration of our carbon monoxide here is not holding up any of the traffic. Basically, as long as there's a reasonable amount of carbon monoxide, as soon as this NO3 gets produced, it's going to immediately get used up. And so what's holding up the traffic here is the production of this NO3. And since that's our slow step, the overall rate depends on the reaction rate law for that elementary step. So that's why we might see something that's zero order with respect to one of our reactants, like we're seeing here. It's behind the rate limiting step, and so we don't have to wait around for it to do anything. We can draw out an energy diagram as well for rate determining steps. So in this diagram, we've got our reaction progress on the x-axis as we're moving left to right. We're getting further along in the reaction. And our energy is increasing as we go up the y-axis. So we come into this first transition state. We've got a very high activation energy here relative to our second activation energy. And so this is going to be the big hurdle. Once we've gotten up this big hill, this big activation energy, that's the biggest barrier to overcome. And as long as it comes down into this little trough after the first step, it should be a lot easier to get up over that second activation energy, because it's a much smaller activation energy. So the first step, the slow step, here is determining our overall rate. And that's why we get the same rate law as the experimental data. In order for us to have a valid mechanism, we've got two important points. Those two important points are that the elementary steps, those individual steps, have to sum to the overall reaction. So we've got to check and make sure we've got all of our reactants that we're expecting on the left side, we've got all of our products that we're expecting on the right side, and our intermediates show up on both sides in at least some elementary step. So we can cancel those all out, add them up, subtract them out. And then our rate law predicted by the mechanism has to be consistent with the experimentally observed rate law. So the rate law predicted from the elementary steps has to add up to agree with our experimentally observed rate law. And we can't prove these mechanisms like for sure. We can't be like, yeah, 100% this is what's happening. But we can say, yeah, that seems like it could be a valid mechanism, and then we would do more research, do other types of experiments to figure out whether those steps keep making sense, or maybe there's an alternative mechanism that also fulfills the conditions that we've set. Any questions so far? So when a mechanism begins with a fast initial step, our rate law for the rate limiting step may contain reaction intermediates. And a rate law that contains intermediates can't correspond to an experimental rate law. Any ideas why that is? Yeah, it's produced and then it's consumed later in the process. It doesn't show up in our overall reaction. It goes into making something else. If our first step is fast enough, then we can establish an equilibrium. An equilibrium, in case you've forgotten, equal rates forward and backward. And the result of that is that the reactants and the products concentrations aren't changing. They're not going to be the same. We might have a lot of one and a little bit of the other, but those concentrations over time are not going to change because the rates of change are equal. So if we have a fast initial step, like in this reaction, and then a slow step, and then another fast step, this fast step is at equilibrium. And now these first two steps show up in the, or both contribute to the overall rate law. So we've got our overall reaction up at the top. We did an experiment. We figured out that our observed rate law is this. We've come up with some ideas, or somebody's come up with some ideas for us about what our steps might be. And we've determined magically that they're fast, slow, and fast respectively. The first thing we want to do is show that our elementary steps work, that this mechanism works because the steps add up to the overall reaction. We're screaming through this lecture, maybe inside our heads at least. So I'm going to give you some time to show that condition 1 is met, and then we'll do it together. All right, so first thing we might want to start with is crossing out any of our intermediates. So looking for things that exist, show up on the right side of one of our early reactions and show up on the left side, one of our later steps. So this N2O2 shows up on both sides. So we can cross that one out. Other things that show up on both sides. We've got N2O that shows up on both sides. So we can strike through our N2O. And what's left, we've got 2NO, which we see in our overall reaction. We've got our 2 H2s, also seen in the overall reaction. On the product side, we've got 2 H2Os, and we've also got an N2. So this does meet condition 1. Our overall steps do add up to the overall reaction. That's the easier of the two, perhaps. Condition 2, we need to show that our rate law predicted by the mechanism, the overall predicted by the mechanism, our elementary steps, is consistent with our observed rate law. So this is where we get to have some fun. For our elementary steps, we can just write out our rate laws. So for this fast step, this is a little tricky because we've got this equilibrium that helps us out here. So our rate is equal to, for the 2NO, K, we'll call it K1 because it's the first step, times the concentration of NO raised to the second power because of that coefficient of 2. We can also do a similar thing for our step 2. We'll go ahead and call it rate 2 just to make sure that it's different. And we'll call our rate constant K2. And then we have concentration of H2 times concentration of N2O2. If we just combine those two steps, we combine these two rates, there's a problem. What's the problem? The N2O2. We can't have N2O2 show up in our overall rate law because it's an intermediate. So we must get rid of or eliminate the intermediate. And that's where it's helpful that we've got this equilibrium. So we've got a forward step, that's our K1NO2 or NO squared. But there's also another step. And since we're at equilibrium, those steps are moving at the same rate. That other step is N2O2 going back to reform our 2NO. So we'll call this K minus 1 because it's step 1 but in the opposite direction. N2O2. So again, this is possible because we've got equilibrium, so our forward and backwards rates are equal, and that's how we get to draw in this equal sign. And then it's just algebra. So we can get this concentration of N2O2 by itself, and then plug in whatever that's equal to. So rewriting that first step, we can write it as K1 NO squared over K minus 1, and that's equal to concentration of N2O2. And then we can substitute this in for our N2O2. So our rate equals, I'm going to lump all the K's together. So we'll have K1, K2 over K minus 1. We've got our H2, and we've still got our NO squared. This looks pretty similar to our overall reaction or our overall rate equation, except for one thing. What's our one thing that's different?
The K's.
All the K's.
K's cancel out.
So the K's, since they're rate constants, these are basically just numbers that have to do with the rates of different steps. We don't know what the individual numbers are, but if we combine them all together, that should give us some overall rate constant. So we can just smush those together. Let's do that in orange. Go Tigers. So we'll just turn that into some K with whatever subscript you want. It doesn't really matter. You could even call it K prime, the superior K.
Can we not cancel out K1 and K minus 1 because they're the same rate? Forward and back? Could be the same thing, right? Or no?
So the forward and backward steps, these two things are the same, but that doesn't mean that the concentrations are the same or that the concentrations are adding up to be the same. So the rate constants could be different. They're probably different. It's a good thought. Oh, good, I didn't erase this. Pay no attention to the man behind the curtain. Okay, ozone naturally decomposes. Before we do that, questions about the previous thing? Ozone, O3, naturally decomposes to oxygen by this reaction. The experimentally determined rate law, the overall rate law, is this. Show that the proposed mechanism is consistent with the experimentally observed rate law. And I will give you some time to give it a shot. So break it down into whatever steps are important and see if you can come up with the same thing. All right, it seems like people are either done or stalled out maybe. So we'll go ahead and get started. So I wrote condition 1 and condition 2 up at the top just to kind of give you some things to think about based on the example that we just went over. So our condition 1 is that the elementary steps add up. If you tell me a story about how you went to the grocery store and your story is, I got in the car, I bought milk, I got out of the car, I've got concerns about where you parked your car. Yeah, you must have parked your car inside the store right next to the cashier, and the dairy aisle is for some reason right there too. So that's concerning. All right, so all the steps in our story of how these chemicals came to be need to add up. So we're looking for 2 O3, 2 ozones going to 3 oxygens. We've got 1 intermediate, that's atomic oxygen. If we add up the rest, then that works out to be consistent with our overall reaction. So that's perfect. Step 1 checks out. Step 2, reaction mechanism consistent, reaction mechanism for elementary steps consistent with overall reaction, or something like that. So we need to make sure that our proposed mechanism, all of our little steps, all of our rate laws add up to get us this final rate law. For our first step, we've got 1 fast step, so that's definitely going to be included. We've also got a slow step, and we're going to be doing some of that same algebra stuff that we did like on the previous slide. So for step 1, we've got rate 1. Rate 1, in the forward direction, we've got O3. So K1, concentration, O3. It's just splitting in pieces. And it produces O2 and O. And we very importantly have that at equilibrium, and so we can write that these two rates are equal. So K minus 1, that's the reverse reaction. We get our O2, we get our atomic oxygen. So that's our rates for step 1. And we also have a rate for step 2. For step 2, we've got O3 and oxygen, so ozone and atomic oxygen. So K2 times our first reactant times the concentration of our second reactant, which is our intermediate. And then we have to rearrange to get rid of that intermediate. So we're going to rearrange this rate 1 so that we can use it to substitute out. So we do that. I trust that we can all do algebra. If you can't, that's fine, just ask. And we'll get you the help you need. So if I'm not crazy, it turns into this. K1 over K minus 1 concentration of ozone over the concentration of oxygen. And we can plug this in where we've got our concentration of atomic oxygen. So the rate equals K2, K1 over K minus 1, which we know that we can lump that all into one rate constant. So poof, it's just K. And we also have O3 in green, O3 in red, and on the bottom, O2 in green. Of course, the color doesn't matter. It's just to show you where they came from. So the two O3s on the top, concentration of O3 squared. So K, concentration of ozone squared, and our oxygen is on the bottom, so that's -1. In classic fashion, I've run out of room. So it's squeezed in there. But that's what it looks like. And this is consistent with our experimentally determined rate law. So that means we did it correctly. Questions about how we did any of that?
For the rate 2, you use the molecules on the second.
Yes. Yeah, so for rate 2, the ozone and the atomic oxygen,
Okay.
since we've got just one of each and it's an elementary step, they've exponents of 1. Other question?
If it doesn't line up, then what? We just say it doesn't? Or
If it doesn't line up, then yeah, you would say it's not a good proposed mechanism, or you would double, triple check your work, depending on the context. All right, here's another generic one. Predict the overall reaction and rate law that results from the following two-step mechanism. And I'll give you a minute or two for this one. All right, first thing that we want to answer, the overall reaction. What's our overall reaction going to look like?
everything without the A subscript 2.
Yeah, everything without molecular A, we might call it. So 2A plus B goes to A2B. Works for me. And then we have to come up with a rate law. We don't have an experimentally determined rate law because it's A and B. Which of the two steps, one or both, are we going to use to determine our rate law? we're going to use everything up to and including the slow step. Or the rate limiting step. In this case, that's just the rate limiting step. Contributes to the overall predicted rate law. Who said you don't get to write in science? So it's just going to be this slow step that we're looking at. And so our predicted rate law is the same as the rate law for that step. K times the concentration of A squared. Questions?
So if fast was before slow, we would do both of them?
If fast was before slow, then yeah, we would probably do both of them.
But since this is slow first, you just go only up to the slow. Because that's the rate step, right?
Yeah. If we had a fast step before, there's a good chance that it would have that double-headed arrow again. All right, I know you've all been dying to hear about catalysts. So there's some other factors. We've talked about how temperature can increase or decrease depending on how you move it, can affect the rate of a reaction. There's other conditions that can affect the rate of the reaction. Catalysts can also contribute to changing the reaction rate. So a catalyst increases the reaction rate. It's not part of the reaction rate, or not part of the reaction. It can be part of the reaction in a way, but I'm thinking of two different types of catalysts. So our catalyst, the important part is that it doesn't get used up in an ideal world. And it also increases the rate of the reaction, which is great. For example, with ozone breaks down into 2O2 in this elementary step through this transition state. It's got a high activation energy. And so the rate is fairly slow, which is great because we have ozone up in our higher levels of the atmosphere that protect us from bad stuff. And fortunately for us, it does not rapidly decompose into O2 because we actually want it to be O3. However, if you get some chlorine atoms into the mix, then that can produce this catalyzed pathway. And so it's a much lower activation energy, and so it will break down much more rapidly. If you wanted to think about the mathy bits, you could think of the Arrhenius equation. Smaller activation energy is going to result in a faster rate constant. The mechanism for the catalytic destruction of ozone, which sounds cool, is this. So we've got our chlorine coming in and playing a role. Our chlorine latches onto an ozone. It steals one of those atomic oxygens away. So rather than having O2 and atomic oxygen, we've got our chlorine playing a role here. And that speeds things up. And then that chlorine with the oxygen reacts with an atomic oxygen, and chlorine is regenerated. So it does play a role in the mechanism in this case, but it comes back out as chlorine. And so then it can go on to do this step, this reaction again, as a catalyst for another reaction, until eventually it's eaten up by some other secret third process. So showing up here that it's not consumed, we had it at the start, and it shows up again at the end. And these chlorine atoms are formed by the photodissociation. So up in the upper atmosphere, there's a lot of nasty electromagnetic radiation that would damage us. And it also damages chemicals. But chemicals don't have brains, so we don't care about it for the most part. So our chlorines, Cl2, that's up in the atmosphere maybe, gets knocked into pieces. And that's how we get that chlorine. And that's from anthropogenic chlorofluorocarbons, CFCs, like Freon 12 and other refrigerants, primarily. Catalytic converters also use catalysts. This is a different style of catalysts. So these catalysts that are in your catalytic converters, things like platinum, rhodium, and palladium, expensive metals. That's why people steal catalytic converters and sell them for scrap metal. They're plated onto high surface area substrates so that you've got your exhaust coming through, and it's got lots of places to interact with and come in contact with these catalysts, like platinum and rhodium and palladium. And then some of these things that we don't want in our exhaust get turned into less harmful things like N2 and CO2. So it helps improve the combustion of the engine and clean up the stuff that comes out so that we aren't polluting our air quite as much. And in this case, our catalyst just gets written in under our reaction arrow. That's where like reaction conditions and other things will often show up, is below the arrow. Other reactants might show up above the arrow. We've got two main types of catalysts. If you remember back to 3A and maybe even parts of 1A, there are different types of mixtures. There's homogeneous mixtures and heterogeneous mixtures. And those kind of play a role here. It's related. Homogeneous catalysis, they're in the same phase, so they're evenly mixed throughout. Just like a homogeneous mixture. And that's like the chlorine atoms that are up in our upper atmosphere thanks to chlorofluorocarbons. We also have heterogeneous catalysis where they're in different phases. Or not mixed, like in a heterogeneous mixture such as oil and water. And so this would be like in your catalytic converter. Hopefully your catalytic converter is not in the gas phase, but it's reacting with things in the gas phase. One of the reasons that we talk about the homogeneous catalysis, heterogeneous? Huh? Anyway, one of the reasons that we talk about that ozone example and chlorofluorocarbons is because you may have heard in the past, I don't think this is an age thing where I'm like old enough to remember it and you aren't. You may have heard about the hole in the ozone layer. Raise your hand if you heard about the hole in the ozone layer. Okay, great. Whew. So the hole in the ozone layer occurs in the, Arctic Spring? Yeah, in the Arctic Spring. So there's this big hole that forms in the ozone layer, and the ozone layer protects us from ultraviolet light. So because of the way that the bonds are in ozone, these bonds, the 1.5 sort of strength bonds where it has resonance structures, right? Because of the way that that bond is formed, it can absorb energy in that UV spectrum. And if that ozone hole got too big, during the Arctic Spring, if it started contaminating outward, that could have bad implications for us because we already, some of us at least, get pretty burnt when there's a lot of UV rays out. And so if you can imagine those getting cranked up by 10 times or something, we'd be pretty toasty. And so that's because of those chlorine atoms from chlorofluorocarbons that get up into the ice and cause things to break down. And here's more about that. So these polar stratospheric clouds, there's ice particles up there, and those ice particles can catalyze reactions that release chlorine, for example, from this thing. So it releases chlorine, and then the sunlight can cause that to disassociate into atomic chlorine, and then that can go on and do catalysis and stuff. And so there was this big scare because scientists were like, hey, that ozone hole every Arctic spring or Antarctic spring is getting bigger every year, and that's really bad, and why is that happening? And so fortunately, last time I looked, things were on the mend. Things are looking a lot better. There's a thing called the Montreal Protocol. You don't need to know about this. This is just for you, for fun. So the Montreal Protocol has been around, I think, since the 90s. And every couple of years, they re-up it and agree, yeah, we should ban these other things. And so the Montreal Protocol phased out a lot of full chlorofluorocarbons. And this is the world agreed to, most of the world at least, agreed to do this. So a lot of refrigerants that we used to use aren't in use anymore, or in use in much smaller amounts, or they've put in place procedures to catch those instead of just, oh, we're redoing your coolant on your car, your refrigerant, your Freon or whatever, and they just open it up and let it out in the atmosphere. They would capture that now instead and send it somewhere, presumably. So phase out ozone depleting substance use. And since the Montreal Protocol went into effect, that ozone hole has gotten smaller. So we're back on track. We actually can do good things with the environment. Wow. A way that, or one place that catalysis is used is in hydrogenation of bonds. So we've got this ethene molecule, the eth because there's two carbons, and the ene because there's a double bond. That reaction between ethene and hydrogen, trying to get those hydrogens incorporated, hydrogen ink, into our ethane now, that's a pretty slow process because double bonds are strong. However, if you put a fancy metal catalyst in there, that reaction occurs quite rapidly. And that's because the large activation energy is lowered when the reactants adsorb onto the surface. Adsorb is different from absorb. So when it adsorbs, that's like sticking it on the outside instead of sticking it in the inside. And here's what that looks like with pictures. So the 4 steps for our heterogeneous catalysis. Our first step, adsorption. So over here on the left, we've got our ethene. Our ethene hits our finely dissolved, finely divided metal catalyst, and it sticks to the surface, at least for a little bit. And then we've got diffusion. These things that have adsorbed can still move around, but they're in contact with our catalyst. And they move around and bump around until they react. The reactants can form the products. So our hydrogens, for example, can react with our ethene, and then once the reaction's complete, it can pop off. It might be that we get this adsorption and then immediately it desorbs. and no reaction occurs, that's probably also happening. It's not that it is always going to do this reaction when it hits the catalyst. So that's what happens in heterogeneous catalysis. And we're going to talk about enzymes just a little bit. Enzymes are another type of, I think they would fall into the heterogeneous catalysis part. So enzymes are a biological catalyst. One of the issues with being squishy bits of flesh with like temperature limits, if you get too hot, what happens? You die. So we know that we can speed up reaction rates by increasing the temperature, and it might double if you increase it by 10 degrees Celsius, but if you increase your temperature by only like 5 degrees Fahrenheit, everyone gets very concerned and you're very unwell, right? If you're at like 104 degrees Fahrenheit, that's a really bad fever. And so enzymes are a great way around this because they can speed up our reactions without heating us up, without getting too warm. So our reactant molecule, our substrate, binds to the active site of an enzyme thanks to intermolecular forces. And we've got pictures of this coming up. So here's generally what an enzyme binding mechanism might look like. E for enzyme, S for substrate, aka reactant, and then that forms something. It can also just hop off, as shown by this double-headed arrow. And then sometimes that enzyme substrate complex is going to go on to form the enzyme back and also products, one or more. And enzymes are usually specific to just one substrate. So they've got this funny little substrate-shaped hole that the substrate can pop into. And then because of the geometry at the molecular level, it's like a little cradle. It's like a little safe space for our substrate to hang out and relax. And the way that it cradles the substrate stabilizes it. So it's kind of like cozying up in a blanket in a little corner of a room, right? You feel nice and cozy and cradled. It does that for the substrate, and that stabilizes the substrate so that it can go through that reaction without losing too much stability. Stabilizes the transition state. Just another way of saying that it lowers the activation energy. Enzymes play a role in digesting sugar. So for example, sucrose has a high activation energy at body temperature. And the aptly named sucrase catalyzes that reaction. So the common naming convention for enzymes, not that it matters for this class, is that enzymes end in ase. This is not a maxim. It's not always true. But a lot of them end in ase. And like sucrose, sucrase, the name is similar to what it breaks down. So sucrase, for example, catalyzes that reaction of sucrose. Sucrose has two different sugars that are in it, and it helps a bond between them break. So the long and short of it, enzymes are great. They speed up reactions, and they can help do other things like break stuff down that are highly toxic. Or, sorry, they get jammed up by things that are highly toxic. They might also, anyway. Questions? Okay, then that'll do it for kinetics.